Can blue blockers reduce flicker? I only ever hear this question answered with no, they cannot, but they can, so here's how. Flicker is brightness modulated across time. And a very common example is pulse width modulation for LEDs, where the LED comes on and off in rapid succession, and by adjusting how long the on phase is relative to the off phase, we can adjust how bright the light source will be. And brightness, in turn, is some form of weighted summation of all the frequencies within the visible range. Now, if this spectrum is constant through the flicker cycle, then of course by filtering some portion of it out will not change the flicker characteristics. And I think this is the assumption behind the usual answer of saying there is no connection between blue light filters and flicker. Maybe, of course, getting rid of the harshness of blue light can help with symptoms which are similar to that of flicker, but the blue light filter itself will not directly affect flicker. However, for many light sources, this assumption doesn't hold. And there is also chromatic or spectral variation within the flicker cycle. Very obvious examples are color mixing tunable LEDs, or also in displays when subpixel flicker is applied, or temporal dithering for achieving some colors, which is actually made worse by night shift modes. Then the color will change through the cycle. And even for a very simple white LED, this can be a problem, and more often than not, it is a problem, because a simple white LED relies on a blue LED chip overlaid on top of which there is a yellow phosphor layer. So through the pulse width modulation cycle, when current comes on in the LED very rapidly turns on because it reacts quickly, but the phosphor takes much longer time to start to absorb some of this blue light and turn it into its yellow output. So it will only gradually turn on. And so in this first phase, we only have blue light emitted. Then the phosphor much more slowly comes on, and the two then, when both are fully on, mix together to give the characteristic spectral power distribution of white LEDs. However, at some point in the cycle, the blue LED will be turned off, and yet again the same thing happens. The LED's light output decreases very drastically and very quickly, while the yellow phosphor only gradually starts to phase out. And this slow phasing out can even bridge the gap until the next cycle starts and the blue LED chip again comes on. So we have 3 or 4 cycles, blue only, white, then yellow only, and then potentially no light output at all. And in a realistic example, I'll link to an article in the video description below. For instance, with 1000 Hz frequency and 80% duty ratio, the 0.2 milliseconds phosphorescence lifetime of the phosphor can completely bridge this gap between the two on phases of the LED. So if we only look at brightness flicker, then we get a much more favorable flicker characteristic, a much smoother curve of the flicker. And this is what practically all flicker metrics do. They only look at brightness, and in this sense, this light source is better, but it introduced a new problem of chromatic flicker, which is hardly ever measured and very rarely studied. So unfortunately, we also don't know much of its physiological effects, but there's a lot of indication that just as brightness flicker, it can have negative consequences. And so you might say that 1000 Hz is really high, nobody can see that, so what's the problem? That's kind of the assumption behind these metrics as well, which don't look at chromatic flicker of these high frequencies, because whenever we measure the color output, we measure it as an average across time, and so with high frequency, all the detailed composition across time will be averaged out. And indeed, most people cannot perceive this either, so we just see a white light output of the LED. But in some cases, flicker can be perceived well above 1000 Hz, even above 10 times that. And most importantly, when we cannot perceive flicker, it still can have negative consequences. For instance, it slows down reading and decreases reading efficiency and work efficiency on displays. And therefore, it induces fatigue and can induce headaches. And for migraine patients, various colored filters can have a positive effect on their reading comfort. And a likely culprit behind is indeed chromatic flicker. But again, this is not studied very much. Nevertheless, getting back to the original question, if flicker, even brightness flicker, can be reduced by filter glasses. So because a white LED relies on the blue output of the blue LED, and that's a big component that turns rapidly on and off, by filtering that out, you will see more of the slower reacting phosphor, so even brightness flicker can be reduced by filtering out the blue component. And then on top of that, there can be individual symptoms or perceptual or neurological issues related to chromatic flicker itself, and that can also be reduced by filtering out various colors. That's kind of individual and depends very much on the situation, the combination of light source and the sensitivities of the individual. However, if you perceive that your symptoms, which could be attributed to flicker, are better when you are wearing some kind of filter glasses, for instance blue blockers, then absolutely do not believe the usual answer that there cannot be a connection. Blue blockers can indeed reduce flicker.